Hey everyone, welcome to another problem session. Today we have a couple of interesting problems for you. So this has to do with mutual inductance. So all of these concepts are kind of discussed in detail in my website here. So you can go out and check more out there. Before I forget, if you haven't subscribed, please subscribe to this channel so it kind of helps distribute it more. If you like what I'm about to tell you, etc., then don't forget to hit the like button. Appreciate that. Thank you. So now let's see. It looks like the same diagram here, but there are two different problems here. One is, but they're related. Okay, so one is you assume that this is an infinite solenoid with n turns per unit length, and connected to a power source. So this is considered like there's one circuit, and then there is another circuit. It's just a loop of wire. You can say that it's a circuit. So when the current flows in here and it's constant current, there is no current induced in this loop. Loop has no current. This I will call this loop and call this solenoid. Solenoid also has a whole bunch of loops, but just for the sake of nomenclature, consider this as just loop, and this, whenever we're talking about these loops, it's just a solenoid. Okay, so we want to figure out how to tell how much current is going to be induced if this current through solenoid is time dependent, is varying in time. Okay, so first thing notice in this scenario is when dis dt equal to 0, I in the loop is 0. So that's just coming from Faraday law, right? Okay, so we're supposed to say when this is not 0, when this is not 0, then what's L? That's the question, part A. Part B is suppose you now take out power from here and insert there, and this, so solenoid is like becomes the loop now. All right. When you do this and you drive whatever current was function you found over there, maybe just drive the same thing over here. Okay, and the question is what kind of current will induce there. So in this one you'll have a if or when dil dt equal to 0, there will be nothing induced here. Current will go, there's magnetic field, everything, but there's no flux change. And if this is not 0, then the question is, what is this? All right, now you have the question. I'll just give you a hint that magnetic flux. So if I have there are two circuits. So you have a circuit 1 and other one, I'm just going to use another thing for it. So this circuit 2. So if you have a current I of T, then in the other circuit you will have a flux from here induced I1 of T. Let's call I1. So flux in the 2 will be magnetic field created by this. So we just say mutual inductance. This is called mutual inductance. And the current in I1. And so if this is changing, so Faraday law will say, so it will say that EMF in the induced equals to minus d phi 2 over dt. And so you can go out there and then you can see that this is equal to minus this will be EMF induced will be EMF is minus EMF of 2 is minus E2 dot dl. So you go this loop, you integrate this, and that's equal to, if this is minus, then this is plus ddt of b dot n hat dA. So I don't want to put negative there because we're following a convention in which we do this. Okay, so this just over here m di1 dt, and we can use a right hand rule just to figure out the direction of the current that will be induced. Okay, so maybe use Lenz's law for direction. Just going to use this because that's much easier. Just also nice playing around with that. Okay, so I explained, and this is you have to figure out how to get the mutual inductance and things like that. So I'll do all of that out here in this situation, how to get the mutual inductance. Once you get a mutual inductance, you can get EMF induced, and then from the EMF induced you can get the, because the resistance is RL, so if I know how much EMF is induced here, I can get a current inside there. And then we can work out the same way over here. Okay. All right. If you like to, while doing the second one, if you wanted to use some kind of resistance of solenoid for RS, if you wanted to use something like that, that would be fine. Okay. So I will erase this and come back and try to do this problem for you. Okay, so let's tackle this one first. So in this one, and let's look at a cross section. So we're gonna kind of look at a cross section. So in this cross section, here's the loop, and it doesn't have to be centered about this thing. Okay, so, and here is where the solenoid is, and that's where flux of the solenoid is. So it it's coming out, so the B of the solenoid is equals to mu 0 n, and at some time is I solenoid t, and the n hat is that way also because the current is going this way, so n hat is that way. So you can see that the B if I go in dl in this direction, then the n hat is that way for the entire loop. But the only part that matters is flux is where the B is, and the B here is 0. B outside is 0. We assume the solenoid is infinite, although it's not infinite, but I'm just gonna assume it. So when I do Faraday law for loop, going around this loop, so we get a EMF in the loop, in loop. This will be the induced EMF in the loop. We can just call it EL equals to I need to go integrate around this loop in that manner, minus E dot dl. Of course, we don't know all of this, just but the law says that this is equal to plus ddt of b dot n hat over the entire area. So this is the surface. We're talking about this white thing. That's the surface. So over that surface, we're supposed to integrate dA. It's like that, right? But when you do this integration, you are going to get just d dt and b dot n hat over that. So this times n hat, that's going to be mu 0 n ist, that and this area dA, the area does not depend over the solenoid area. Plus 0 outside the solenoid is 0. So over this, let's call it solenoid area SA. So that's the integration I'm going to do, and outside of that it gives me 0. And this whole thing does not depend on where it is. So inside the solenoid, also this thing comes out of the integral, and this just becomes the times the area. So this is just ddt mu naught nis, that depends on t, times the pi a square. So when I work it out, I get a mu naught n pi a square dis dt. So this is the mutual inductance. This is mutual inductance dis dt. And it also, although it looks like asymmetric between this and this, but actually mutual inductance between the two, if I had worked out current in here and flux, induced flux in there, I will still get the same mutual inductance. Okay. So we found out the mutual inductance, which I can use over here. So we found the mutual inductance between solenoid structure and the loop structure. So solenoid and the loop structure is equal to mu naught n pi a square. Okay, so this is the amount that got induced in the loop, although the magnetic field came from the solenoid. Okay, so what's the current in the loop? Induced current in the loop will be this EMF, this EMF over the resistant in the loop, because that's what, like a voltage, acts like a voltage. So M over RL, with M being that, dis dt. Okay, so that's the answer for part A. So this current induced in L is also, could be a function of time if this is not linear. Could be constant, this is linear. Mu naught n pi a square over loop's resistance times the current in the solenoid is time derivative. Okay. Let's try to do the second one. Okay. So to do the second one, it's really not that much work anymore, because according to this, we found that exactly the same kind of relationship would be between the others, like the, E in the solenoid will be M. I'm looking at absolute value d I L dt. So what the current here is with the same mutual inductance. So how much current will be induced here? Well, IS will be ES, the resistance of the whole solenoid, right? So if you work it out, it's going to be this is going to be mu naught n by a square dIL dt, and so this will be mu naught n by a square over rs dIL dt. It's completely symmetric kind of formula. So one circuit, if they are coupled, so this the way we say these circuits are coupled is if magnetic field created in this circuit says CS but says CL, can it go through the area of that loop? Okay, so now if imagine there was a loop like that, CL2. Okay, so this is CL2. This now magnetic field, no magnetic field goes through there, so there will be no, this is uncoupled, this will be uncoupled, and so hence this will be I in this loop 2 will be actually 0. So not every two circuits lying by, next to each other will be coupled. You have to have a magnetic field created by the current in one loop has to pierce the other loop. Same thing over here. This guy is creating magnetic field. You can see right hand, you can see it's going to go like this. So it's going through the loop area. It comes out and goes through loop area. So these magnetic fields created in this area will actually work to induce current in the solenoid. Even if the solenoid doesn't have any current source, you can induce a current through this mechanism. There are lots of applications of this, trying to induce current from a distance, right? So this loop and this loop are not really physically connected, but they are connected through the mechanism of electromagnetic induction. It's very important. This is these kind of problems are very important for you to understand for lots of applications. Okay, so I'm going to stop here. Again, just a reminder that if you haven't subscribed, please subscribe. That helps the channel grow. Like also helps the channel grow. Thank you. Okay, bye bye.